Activity 3.4 concerns the family of functions defined by p of x equals x cubed minus ax, and what happens with this constant a. So first thing we're going to do is we're going to look at the first derivative and see if we have any critical points. So p prime of x, this is not a bad derivative. We just have our power rule here, 3x squared minus ax, that's just a linear term, so it's just minus a. So there's our derivative, and now we're going to set it equal to 0 to find our critical points. So nothing changes from our normal routine there, except our critical points are going to be in terms of a. In solving this, we'd add a to both sides, and we get 3x squared equals a. Divide both sides by 3. We get x squared equals a over 3, and then we'll square root both sides. Now the last thing we'll take into consideration is the positive and negative, square root of a over 3. And so we've got two critical points, one at negative rad a over 3 and one at positive rad a over 3. So let's construct a sign chart. So we'll put one in here, negative square root of a over 3, and one at positive square root of a over 3. Now we're going to assume that a is positive. We'll talk about what happens when it's negative here in a second. So if a is a positive value, we're subtracting it off. And first thing we know is 0 has to be in between these. This is going to be a negative number, this is going to be a positive number. So 0 is a very nice, easy test point. So let's just start with that. If x is 0, we're subtracting off a positive number, which would be negative. And that's our first one. So we know our original function is decreasing on that interval. So this is p, this is p prime, this is p. Okay, what if we use something larger than square root of a over 3? Well, if we use something to this side and it's larger than square root of a over 3, when we square it, we're going to have something larger than a over 3. The 3's will cancel, we'll have something larger than a. Subtracting a is going to leave us with a positive, so our function is increasing at that point. Finally, something smaller than negative rad a over 3. It's going to be very similar to positive rad a over 3 because of the square, so it's going to be a larger magnitude than this. We're going to be multiplying it by 3, which cancels out the 3, so we have something, again, larger than a. It will be positive because of the square, subtracting a, so it will end up being a positive difference. So we've got a relative min for this function at x equals negative square root of a over 3. And we have a relative max at x equals positive. Sorry, I cut those backwards. We have a relative max at negative rad a over 3. We have a relative min at positive rad a over 3, as we can see from our sign chart. Max at negative rad a over 3, min at positive rad a over 3. Now, if a were to be less than 0, think about what would happen. If a is less than 0, then we would be adding something to the end here. For instance, we could say that, okay, well, what if a was negative 2? Let's just look at one example. Our derivative would be 3x squared plus 2, which is 3x squared shifted up 2. This does not have any real zeros, so this would not have any critical points. So in order to have critical points, we needed a to be less than 0. Excuse me, we needed a to be greater than 0. So we don't need to worry about this particular case having critical points, and we'll look at the graph to see how they differ. So there's only critical points in this particular family of functions if a is greater than 0. Lastly, let's examine the concavity by looking at the second derivative of x. So we have just 6x, derivative of 3x squared is 6x. A is just a constant, its derivative is 0. A sign chart here is very easy to make. We have a critical point of our second derivative at 0. And if it's less than 0, if it's a negative, this will be negative. So this is for our second derivative. That means our function will be concave down from negative infinity to 0. Similarly, if we use a positive value, this second derivative will be positive, and it will be concave up from 0 to infinity. Notice there is no a in our second derivative, so this is regardless of what a is. So regardless of the value of a, this is what our concavity will be. So the value of a in this family of functions has nothing to do with the concavity.